Hi, everyone. So last time, 1 second, let me just rearrange my window. Okay, so last time we covered a topic called snapshot. As I mentioned, this lecture and next probably couple lecture will be on a topic I call the file system trio, which is a snapshot, background FSCK, and the soft update. And this three concept, essentially what we're doing is that we want to worry about when the file system crash at any time. And soft update will protect a property about a file system such that at any time you can use the file system safely, even after crash. So we will define that. That's the third topic. So it means that file systems is so important. If you have any kind of crashes, the power down or whatever, you throw your hard disk out of the window, and suddenly the file system kind of in a uncertain state. And the mechanism, the trio, the third element of the trio, basically guarantee that regardless how and when your hard disk crash, there are certain level of consistency that will be maintained. And that, by the way, is very important that you can actually do that. But to require that particular survivability or availability of your file system, there is another requirement that yes, it crashed. I can recover that. But if it's taking so long, if it's taking like 1 hour before I can use my file system after a crash, that might not be desirable as well. So background FSCK is essentially try to recover your file system at the same time. That's why it's called background. You're recovering your file system while you allow the user to use the file system immediately. So the idea of a background FSCK is try to shorten the time the file system became unavailable and such that you use that immediately. And the thing is, how do I actually do the background FSCK? In fact, it's using the first concept we talked about on Tuesday is the snapshot. So essentially, when the file system crash and you want to use the machine again, when you turn on the machine, the first thing you will do before you allow the user to use the file system is you take a snapshot. After you take a snapshot, you actually run FSCK on that snapshot. While after you've done this, so remember I said how long it will take for me to create a snapshot. It's probably less than a quarter second. It's really short. You just create, I know. So that amount of time is really negligible that we feel very comfortable. And you can actually start using the file system while I'm doing background FSCK on that snapshot you just took. Okay, and the thing is, the reason you can use that file system immediately after you take that snapshot before the FCK finish, it was due to the third concept called soft update. So the soft update is actually going to make sure that your file system is always usable, always safe to use, always some level of consistency, which we will learn probably next week. But today, I'm actually going to focus on the second element of the trio called file system integrity check. And what's that and how do we do this in offline? So this is the idea of snapshot. We actually stop here on this slide. Any question before I move on? Oh, I saw a lot of questions on the chat. Let me see. Okay, I'm sorry for uh, the the student are having internet streaming problem. And don't worry, I will record. I have been recording this lecture and the previous lecture. By the way, the Tuesday lecture I haven't uploaded to YouTube yet. I will upload both today's lecture and Tuesday's lecture on YouTube channel, so you can actually try to catch up the gap because of the internet unstability. Okay. Any other question about what we did so far? Okay, so I'm going to talk about the next concept. So I just want to share with you that you can take a multiple snapshot. In the FreeBSD kernel, you are allowed to take about 20 snapshots. And the thing is that the reason there is a limit, because remember, after I take the snapshot, every single file access need to check against all the snapshot you have to decide whether some of the snapshot will trigger copy on write. So that's why you cannot support. This is kind of limitation on the snapshot issue, just to let you know. Skip and just let you know, this is the source code. If you're on a FreeBSD operating system, this is the source code. This is in the kernel. I mentioned that Snapshot is a service being introduced in the kernel, and the kernel, they will preserve the snapshot. They will also doing all this other code when you want to do copy on write. Okay, so this is under Unix file system. There are two directories, by the way. One is a UFS, one is FFS. FFS stands for fast file system, which is essentially the inode and also the services like Snapshot related to the inode will be always put under FFS. And there is another directory called UFS/UFS that is actually handling the things like a directory entry, and all this other related services is over there. Okay, and so we actually show that how Snapshot can be used for backup and restore, and you basically can dump a very quick, with a very short amount of time, an active file system. When I say an active file system, means that I make sure that the unavailability of the file system is very short when I actually try to do the snapshot. And the fourth point I already mentioned earlier today, that the one very important application of Snapshot is try to support the concept of background FSCK. Okay, so now we're going to take a look. In fact, if you understand Snapshot, the difference between FSCK and background FSCK is not that difficult to understand. So first, I want to introduce the concept of FSCK itself. What do I mean by file system consistency check? Okay, so so this is the picture, which is maybe is a simplified picture of a kernel. So you can see that the kernel is in the middle, and then you have application, and then you have your hardware. So your hard disk is on your hardware. So that's your real file system is actually hosting your file. It's permanent, and that is a place when you want to retrieve everything. That's your file database. And the application is actually going to do read and write to this file. But pretty much any modern system have this problem called buffer cache inconsistency problem. The thing is that in order for us to achieve higher performance in information access or disk access, we always cache the disk blocks that you're interested to access to memory. And in fact, some of this is to the cache memory. So you have your cache memory. This is under memory hierarchy. Whenever you want to access, it's always in the cache. And some of this, it might be in the main memory. Okay, and then of course, this is reflect what's going on. in the hard disk. And the challenge over here is that we need to maintain what we call a coherence or consistency problem among those few copies on all different layers of memory hierarchy. So in some sense, when you read it to the cache, and I actually modify, and so now the copy you have in cache is different from what you have on hard disk. So now you have an inconsistency problem until you synchronize, until you write it back to the hard disk. And then make sure you write back to the hard disk in a way that is consistent such that your hard disk and your memory are exactly the same. In fact, there is, as I mentioned, there are other block you need to write when you write back. Because when you modify a particular file, it's not just you're going to modify that particular data block in hard disk. In fact, you need to modify your inode block because inode will contain a timestamp represent when this file was last modified, for example. And there may be other kind of changes you need to modify, and such that variety of data structure within the whole file system need to be updated between the hard disk and the memory. And just to let you know that every time you do something about the file, it's not just the data block. It has a lot of other type of block that might need to be changed as well. Okay, so the whole thing about file system buffer cache consistency problem is become more interesting when our system can crash at any time. So you're actually doing this synchronization between your memory and the hard disk, and suddenly in the middle of nowhere, I don't know what happened, somebody kicked the power cable, and basically the whole power is gone. The power is gone means that all the stuff that you have in the memory is gone. And the thing is that you don't know when was the last disk write to the hard disk. So there is a risk that you actually have something which is in the middle. And when you actually turn the machine back up, how do you actually guarantee your file system is still usable? It's still safe to use, double quote. Okay, so that's the issue we want to do. And there are multiple approaches to deal with this. But the first approach we're going to talk about is called file system consistency check. So our objective.
Professor, I have a question.
Sure, go ahead.
In the previous slide, so whenever you're writing the files back into the hard disk, will the files first get stored in the buffer cache and then go, or like, I didn't understand that, but can you re-explain that?
So it's always right back for performance reason. So okay, that's a good question. Okay, so the modern system is always write to the cache first. In fact, it will delay all the write to the hard disk until your CPU scheduling decide that, okay, now is the time for us to write back to the hard disk. So there is a delay process between when your application write it to the buffer cache until this buffer cache got reflected, get written back to the hard disk. Most of the modern system took this approach. There are some earlier Unix file system, what they did is they write back immediately. So when you read into the buffer, but anytime you change the buffer cache, because of the case you want to change, it actually trigger that you have to write back to the hard disk immediately. So, but that is sometimes has some performance issue, to say the least, and therefore most of the system didn't take that particular approach. Okay. Any other question?
I have a question.
Sure, go ahead.
So does the buffer cache maintain only modified blocks, or does it also track the modified inodes to change as well, such as modified
Yes,
timestamps?
uh, it actually maintain. Also the inode block, everything is need to be cached as well. Yeah, everything, including data block, including all this inode block, whatever directory block, everything need to be changed. It will be actually changed in the buffer cache.
Okay, thank you.
You're welcome. Any other question?
Yes, Professor, I have a question. So
Sure.
does the buffer cache maintain a set of dirty bits to make sure to keep a track of what data has been modified in the cache itself?
Yes, definitely. Yes, it has the dirty bit. Yeah. Okay. Any other question?
Professor, what is typically the size of a buffer cache in with respect to your system? Does it depend on the size of the hard disk, or is it something constant?
It's depending on the computer architecture. So you have a different level of cache. You have level 1, level 2, different kind of cache. And the thing is that it depending on the size of your machine. And typically the newer CPU is actually trying getting a bigger cache. And the thing is that in memory management, some of this cache needs to be right back to the main memory as well. So it's not always everything is on the cache, because whenever you're running out of cache space, you're going to push them to the main memory. If the main memory also have something not enough, that's called page fall. And then so you have a cache miss, you have a page fall. So that's the memory management issue. Okay. Okay. Okay, so let's try to worry about how to maintain the file system consistency. And the thing is that is important. I actually write it here. The ordering of update from the buffer cache to the disk is critical, because we have different kind of structure. We have a data block, we have a directory block, we have inode block, right? So this is just let you know that this is example. If you actually update the directory block first, then you update the inode block, then there is a possibility your directory structure will be inconsistent, because you already modify your inode. Your inode is no longer that particular number, which your directory block is actually still pointing to that number, but the system crash before the inode block is updated, then essentially your directory structure is inconsistent to the inode information you have there. So we'll see a clear example in this to just give you a heads up about what's going on. So when we do the update, you actually make sure that you have to update inode first before you update the directory block. So that's the kind of ordering is very important. Okay, I'm actually going to talk about different strategy. So the first strategy is basically don't have any buffered IO. So whenever you want to write something back, especially it's related to the metadata, which is inode and pointer block, you always write immediately. So this essentially force the file system to be really consistent. And it's, by the way, it's not guaranteed, because even though you try to do that, but that process still have some chance, small chance to crash right at that moment. So therefore, you have to do some other thing to make sure that in the prevention approach, it's still maintain the consistency. So the overall goal is that the file system need to design in a way, regardless prevention or the detection and fix approach, you have to consider the worst case, the worst timing that your file system crash, and then what you're going to do about that. Okay, so the first approach is try to minimize that risk, and with that small risk remaining, you want to do something special to deal with that. But most of the modern systems are taking the second approach. is called detect and fix. So I have some way to actually be able to tracking the consistency of the system such that I can determine there are some inconsistency. And when you actually detect that inconsistency, then you apply a set of rule to actually fix those inconsistency in your hard disk, in your file system. That's called FSCK. FSCK stands for File System Checker. So we're going to talk about FSCK first, then we want to see, well, how do you do background FSCK? So I'm going to talk about two different kind of file system consistency check. One is called block consistency check. One is called file consistency check, which is also related to the directory structure consistency check. So let's actually take a look at the first one. It's called block consistency check. So remember, we have a free block bitmap. So there is a data structure. Here I call a free list table. Actually, I should modify this because I want to use the consistency in my own slides. So there is a one data structure called free list bitmap. Okay, we already know that. We have to have that because operating system need to know on your hard disk which block is actually free to use. So the second line of here is actually going to tell you that's actually going to be 1, that means it's a free, and 0 is not free. Okay. So what I'm going to do, I'm actually going to create a second bitmap. The second bitmap, in fact, you will see that it's actually not a bitmap, it's actually an integer array. Well, yes, it has to be an integer array. At least conceptually, it needs to be. So essentially, this is called block in use. Let's first talk about it's a bitmap. Block in use bitmap. So means that I want to have another table which actually tell me whether this block is in use. So the first table basically tell me which block is free, but I want to have another table which tell me which block is in use. You might feel kind of funny when I'm saying this because isn't this two duplicate? Isn't the first table and the second table supposed to come up with exactly the same information? That's true when your block consistency is indeed perfect. Okay, so the thing is that it's supposed to be like this. If I haven't tell you how I'm going to construct the first table, but if everything is perfect, it should be 0, 1, or 1, 0, essentially, between these two tables. And there are conditions where they are inconsistent. So you will have a 0, 0, or a particular block, you have a 1, 1, or you have a 2, 0. That's the possibility. Okay. So we're going to have a two tables. So the first table, or the second table, sorry, we already know that it's there. It's called free list bitmap. Okay, so now I'm actually going to talk about the first table I call block in use table. Can some of you guess, how do I actually construct this table? How do I actually construct the first table?
Using the end link.
How do I use n links?
If it is 0 and the block is not being used by anyone.
Oh, n links, by the way, the idea of n link is not about block. The idea of n link is how many directory entry is pointing to inode. But you're hitting the right direction, by the way. Remember, let me actually go back to this picture. Let's go back to our favorite data structure. I know. Remember, this is I know that we talk about. I hope you understand. There is a lots of pointer. So if there is a one pointer over here, it actually pointing to a particular disk block. Then essentially this particular block is in use, right? So if I have a one pointer in the direct, single, double, triple indirection, that's actually pointing to a particular block, then that block is in use. So what I'm saying is, how do I actually construct the first table? I am going to examine every single I know in my file system and examine every single pointer in each of the I know and against every single data block on the right-hand side. And therefore, if there is at least one pointer, then I know that particular block is in use. On the other hand, if none of the I know has a pointer pointing to a particular block, then that block is considered free. Does that make sense? So essentially what we're doing is we're actually looking at I know. And that's why FSCK, by the way, is very expensive. I actually use the operating system before background FSCK is available. Before, like, I forgot exactly when it was introduced. It must introduce in the somewhere maybe around 2000 or earlier, maybe 1995. So I was working on the earlier version of Linux, FreeBSD, and Mac operating system as a PhD student. I was working on that operating system kernel about 1990, 1991. And I remember because I modified the kernel a lot, so my kernel panic, my kernel crash anytime. And every time it crashed, it need to do a FSCK. Anytime I do a FSCK, I actually need to take a 30 minutes break because I need to go out to get some coffee because FSCK took a while before it can finish. And just let you know, my hard disk at that time is about 384 megabyte, not gigabyte, megabyte. That was the hard disk. It's already considered pretty big in 1990, 30 years ago. And that hard disk, 384 megabyte hard disk, it took a half an hour to do FSCK. So that's why it's expensive. Why just look at this? I need to actually go through every single I know and do a counting on every single block to see if that particular block is free or in use. Okay. So now I'm going back to my slides here.
Professor, I have a question.
Go ahead.
So the block use count is generated each time the check begins? The block in use table?
The block in use table is actually generated when you perform FSCK, file system consistency check. You don't need this table. This table is not there maintained at the normal time. This table, the second table, is maintained all the time because you need this data structure to manage your hard disk. But the first table is only produced when you're going to perform FSCK. Does that make sense?
Yeah.
Okay, so I'm saying that it's quite expensive, all right, because you need to go through every single pointer in every single I know. Okay, it took a while. Okay, so the thing is that after you construct—
Professor, I have a question.
Sure, go ahead.
So when you're producing the block and use table, you said like to do that, you'll go through every single inode and see if it points to a particular block of or a particular inode and see, if it can be reached.
Right.
And if it cannot be reached by any other block, then, well, there's no link, or it's a free block.
Right.
But what if that free block that cannot be reached by anything else points to another block? Let's say, just one other block. Well, the free block points to also be considered free.
If I understand your question correctly, if a block, there's no inode pointer pointing to that means a 0. So essentially, I create an integer array. Each of the element represent this block number. So this is a block number 1, block number 2, block number 3 on my file system, right? So essentially, I'm actually create an integer array. That's why I said integer array. So every time I actually, by the way, initially everything is a 0. When you actually encounter inode pointer pointing to this block, you +1. So suppose your file system is consistent, then the block consistency, then your value should be just a 0 and 1, because there should be only one file, one inode has one pointer pointing to an in-use block. If this is in use, if this block is actually not in use, it's a free, then there should be none of the pointer, should be 0. So ideally, that the value of the block in use table, the value should be just 0 and 1. Okay. However, there are cases which I will explain to you the reason that you're going to have a case which you might have 2, 0. Means that, what does 2, 0 means? Means that you have two different inode, or the single inode with two different indirect pointer, they are pointing exactly at the same block. So think about, you're actually watching the movie called Superman Return. And then you have a homework assignment for ecs251 on the JSON RPC. And you realize there's one disk block that's actually shared between Superman Return and your JSON library. That's basically really, really inconsistent, and it's probably very dangerous when you have a 2 over here. Okay, but it could happen, right? You actually search for all your inode pointer, you realize that there is a pointer that's actually pointing to the same block. Okay. Any other question?
Professor, can you just repeat when is it possible for the for two inodes to point towards the same block? I didn't get it properly.
No, I haven't actually talked about that yet. I just say it's possible, but we will look at the case. We'll look at the case. Don't worry. Yeah. We'll look at case actually immediately. Okay. Let me actually first forget about 2, 0. Okay, forget about 2, 0. So number one, I just want to summarize. If this corresponds to this block, number 1, number 2, number 3. Okay. So if it's consistent, block consistent, it should be 0, 1 or 1, 0, right? Well, if it's inconsistent, let's forget about 2, 0, but has a 0, 0 and 1, 1. So 0, 0 means that the block in use table says there's nobody using that, but the free list bitmap saying that, sorry, this block is not free. Or you have 1, 1, which your block in use table say, hey, I have a 1 pointer that's actually pointing to this block. And however, your free list bitmap is basically say, it's actually a free block. So, okay, I actually make another mistake, I realize. 1 second. It's not free list bitmap, it's free block bitmap. Free block bitmap, sorry. So there is a case is 1, 1 and or 0, 0. Okay, so let me ask you a question. Which of this two kind of arrow is more serious? Or which kind of the arrow is actually much more dangerous than the other? 0, 0 or 1, 1? Which case do you think is worse? Much worse, by the way.
I think maybe it's 1, 1 because you have a possibility of your data being overwritten.
Exactly. So if it's a 0, 0, what we worry about is, okay, you just have a one particular block. It should be free, but it's not free. I cannot use it. So typically today, the modern hard disk is getting bigger and bigger. And so missing 1 or 2 block, it doesn't matter. I can still use my file system without any problem. But 1, 1 is really bad because 1, 1 essentially saying that you have a file, which in that case is the movie of Superman Return. And it's actually used this block. And the thing is that, however, the free block bitmap is actually put a 1 there, means that this block is available. So now you're actually working on your homework assignment number 1 with JSON RPC. You suddenly want to compile code, generate executable. You're going to produce a file that needs a new block. And guess what? The operating system just so lucky, pick this free block assigned to you. And so now you actually write your homework assignment number 1 to that particular block. Guess what? Now after that is finished, you have 2, 0. So that's the thing is, the reason you have 2, 0 is because you first have a 1, 1. So the thing is that 0, 0 is not ideal, but is acceptable, or we can live with it, at least for a while. But 1, 1 is actually definitely something need to be prohibited. It cannot happen. If 1, 1 happen, you will be in trouble. You either lost your homework assignment or you actually lost your important content, such as a movie that you have, okay? And any question? Okay, so I want to summarize this, is that you need to learn 3 things in this subject. Number 1, what is a block consistency? Number 2, how to construct the data structure. In this case, is a block in use table in order for you to check the consistency. So our goal is checking the block consistency. You need to know how to actually compute that table to perform the consistency. The third thing you need to learn is that once you have the arrow, some of the arrow is more serious than the other kind of arrow. So this actually will be really important for us to think about the third of the trio, which is self-update. Is trying to self-update in a very simple way to say is that it will prevent, make sure there's no way that you actually have a 1, 1, but it actually allow 0, 0 to happen sometime. But they definitely, the whole system design is definitely, there is no chance for 1, 1 to ever occur. Okay, so that's my quick introduction to block consistency. Any question? Okay, so let me just move to the next slide, just show you some of the picture. I move it really fast. So, so this is what I picked it up from a typical textbook about what's going on. And so you can see that there are 4 situations. Like this situation, number A is basically consistent, because blocks in use and free block speed map, they're exactly 1, 0. And B is a case that is mostly consistent, but you have block number 2 is actually 0, 0. So we basically have a missing block over there. And the picture number 3, I believe, that you have a duplicate block, duplicate case. Wait a minute. They miss one important error cases. They basically say it's a 2-0, means that the free block is actually 2. This is 1. This is duplicate, and then they have a 2-0 this way. I just realized in this picture, they actually miss a very important case, which is I'm going to talk about is a 1-1. Okay. Okay, so I'm going to go back to talk about the second type of consistency problem, which is, I call it file or directory consistency. So in each of the inode, that you have a number called nlinks, which nlinks represent how many directory entry is actually pointing at this particular inode. And then I can go to every single directory entry called duran to actually build a table. Looks like is a block in use table, but this one I will call it the count of directory entry pointing at this inode table for every single inode. Okay, so essentially we're actually looking at for each of the inode whether the number of incoming pointer is the same as a value of the nlinks, and we're going to do that for every single inode as well. Okay, this is the second part. This is not as bad as a block consistency, because block consistency you need to check every single block pointer. Over here, we only check for every single inode and every single directory entry. And you have to basically, the nlink is easy because you just go through every single inode and retrieve that data. But the directory entry is actually harder because you need to go through the root of the file system, which is inode number 2. And then you have to go down, access every single directory entry about the whole tree, and then you perform the test. And I'm actually using the number D, capital D, and capital L. So capital D represent the answer you got from the first line, the first bullet here. Basically say, what's the number of directory entry that's actually have a pointer to this particular inode. And remember, just remind you, what's the directory entry? Directory entry, every entry has 2 attributes. One is what? The name of the file. The second one is the the inode number. So you go through every single directory entry for this inode, and then you basically construct this capital D for each of the inode. And then for that inode, you have an L. L basically is nlinks. That is already included in that 256 bytes of the data structure, counting on how many hard links that you have that going into that. So you have a D, you have an L. Again, I'm going to ask you the question. If the directory structure is consistent, then essentially D, capital D should be the same as L, right? The nlinks number should be exactly corresponding to the number of directory entry is pointing at this particular inode. So that is when you're consistent. When the file system is not consistent, you have either L greater than D or D greater than L. Okay, L greater than D and D greater than L. So I'm going to ask you another question similar to the one I asked you earlier. Which one is more serious? L greater than D or D is greater than L?
L greater than D.
Is more dangerous or less dangerous?
I think it's more dangerous because if there is a link and there is no directory entry, it might be that we might have lost access to that data overall.
Anybody else have a different thought or the similar idea? Let me see. Somebody might have said something on the chat. Okay, no. Okay, I want to ask you a question, everybody. When do we need to use this information about n-links? So let's actually take a look. Let me actually go do this. Let me cancel it. Insert.
While deleting the file
Exactly. I have I know, okay? And this particular I know, let's say I know, I have I know, this I know called X. And case one, that the n-links of X is equal to 2, where there's only one directory entry. Durand is actually pointing to X. And case 2, n-links of X is equal to 1. But there are 2 Durand. That's actually pointing to X. Okay, so we have 2 different cases like this. So the first question, of course, is L is greater than D. And the case 2 is D greater than L.
I think case 2 is more serious.
That's right.
I think because maybe
On
if
deleting.
if the operating system deletes the file and then someone accesses that block and overwrites that block.
Right.
It
So
might be done.
that's you guys are right now you get it right. D greater than L is actually more dangerous. Here's why. Because if somebody actually tried to remove X, remove the file, basically, file represented by X. And this must be removed by one of the 2 Durand, right? One of the 2 Durand. It must be removing from one of the 2 Durand. Remember in the file hierarchy we show you, there are actually 2, let me actually bring back the slide very quickly. Bear with me. And if you remember this particular hierarchy, that I know number 9 has 2 directory entry. One is VI, one is called EX. They both pointing at the same I node. So in this case, D is 2 because you have a 2 directory entry. So if I remove it, where's my here? If you remove this, what's going to happen after you do the remove, then your D is actually going to be 1. But your n-links, which is your L, or L, is going to be what? Remove it, it's going to be 0. And remember, when we're going to use the n-links is whether this file, the inode and the whatever directory entry can be permanently removed. So D greater than L is dangerous because if somebody actually remove the file, you'll have the possibility that you permanently remove some important file to your file system. I mean, this will happen not necessarily like a remove. Let me give you a scenario this could easily happen. Is when you try to move one file from one directory to another directory. I mean, just how often did you do this? Move one file from one folder to the other. And there's a short amount of time, you're actually going to see you have a 2 directory entry, one from the old directory, one from the new directory. And the n-links after the move is going to supposed to be 1. But somehow the data structure messed up or the timing messed up that you're going to have n-link is equal to 1, but you have a both directory is pointing to this X. And if you don't handle it correctly, that file could be permanently lost because of this 2 to 1, D greater than L issue. Well, let's just be careful. Look at the other case, which is why I said L is greater than D is actually not ideal, but it's totally, I can live with it. Because what's going to happen is the same thing. If now what happened if I remove the file? If I remove X, I'm going to do the same thing. See, it's always a trouble when you try to remove a file or overwrite something. Guess what? If you remove the file, what's going to happen? When you remove the file, I'm sorry that the unlinks is going to be from 2 to 1. So now unlinks of X is going to be equal to 1. When it's going to equal to 1, the file system will not remove this file permanently. It's going to be in your file system for a while until we do something called garbage collection. I haven't talked about garbage collection, but we'll talk about that later. So the thing is that this file, because there's only one directory entry really pointing at this particular inode, and I removed that already, but my L messed up somehow. It says 2. And therefore, when you remove the file, I'm sorry that this file will not be removed from the hard disk. It will be there until you do garbage collection. So compare this two. One is you're going to lose some disk space, but the other case, you're going to miss. You're going to have lost the whole entire file. Okay, so now let's actually go back to this particular picture. Now, these two I list together because they have exactly the same design principle. Both of them are actually checking with two different data structure to see if they're consistent with each other. And both of them has two important type of error. And it's always one type of error is actually going to introduce some really bad situation for your data. And the other arrow, which is okay because you're just wasting some disk space. All right, so what is FSCK, by the way? FSCK is trying to fix the problem. So number one is it will detect this problem, and number two is actually going to try to clear the hard disk. It will detect the problem and try to fix it. Either I have to fix the 1.1 issue or fix the 0.0 issue. And the thing is that that's what FSCK is trying to do, is try to detect this problem and try to fix it. Okay, any question? Okay, so I assume you know FSCK. Now I can move to my next topic.
Professor, I have a question.
Go ahead.
In free block bitmap, what does it mean if the counter is 2?
Okay, free block bitmap, it won't have 2. Free block bitmap is actually a binary array. It's actually maintained by the file system, so the value could only be 0 and 1. It's actually being maintained by the operating system as we allocate the hard disk. It's only when the first table, block in use table, is computed, you could have more than 1. Okay. This table, it's impossible for you to have 2 because it's the data structure. If you look at the operating system source code and how they keep it, they only allocate 1 bit. They only allocate 1 bit. You can only assign either 0 or 1 to that particular bit.
Yeah, but in the next slide, I think the array has 2.
No, this is actually incorrect. I don't think they actually at least remember I got it from a textbook. It's probably not a textbook of FreeBSD, and this one, I think they're the okay. I probably shouldn't say that, but I think the author, whoever drew this picture, they probably never look at the source code of the operating system. if you think about that, how is this two table get constructed? This table, the second table, is always there because operating system, you need to use that. And therefore, you shouldn't have this two because you don't need to, because every block should be only free or not free. Yeah, but by the way, you're good. I never actually pay attention to this two. I just copy it, and thank you for pointing out. Yeah, it's actually that is not at least to the operating system implementation I have a look at. It's never the case. That's why we don't call it free block. We call it free block bitmap because it's only binary. Okay, it's a good catch. Yeah. Any other question? Okay. Okay, so now I'm actually going to go through the third trio. I'm actually going to look at something called metadata operation. So what is a metadata? In a file system, you have your data block. That's not metadata. That's the data really related to your file. But pretty much everything else is metadata, including your inode, including your free block bitmap, including your free inode bitmap, including your directory entry. They are all metadata. And the thing is that metadata is actually maintaining the integrity of your file system. If your metadata get messed up, then basically you might lose the whole file system. If you lost some part of your data, it might be okay because you can have a recovery, you have a way to actually retrieve the older copy. But if you lost your directory, your metadata in a bad way, then potentially you're going to lose a large amount of file because you don't know where they are. Okay, so that's the meta operation. So I'm actually going to talk about this, about the metadata integrity. The first design of FFS, fast file system, they use synchronous write to guarantee the integrity of the metadata, meaning that if you write to a data block, I might delay the write back to the hard disk for the cache and the disk consistency problem. But if you, anytime you write to a metadata, then I request you must write back to the hard disk immediately. And so you want to actually guarantee the integrity, consistency about the metadata, everything of that. Okay, so but the issue is always, if you want to do this, that means you're going to spend a lot of time on IO, and therefore it's always a performance hit. So therefore, we're always thinking, well, can we actually also perform delay write on the synchronous, on the metadata, and such that I can maintain my metadata to be consistent, and then yet I can actually save some performance. That is the issue that we're going to talk about, the next topic, the third trio. So the thing is that the idea of a soft update is the following. Of course, it's delay write because we don't want to write back to the hard disk immediately for the metadata. And the thing is that we actually want to leverage some kind of dependency information among inode block, free block bitmap, free inode bitmap, as well as directory entry. So we want to actually worry about the dependency information about those data structure, and then we try to come up with a correct order for us to write it back to the hard disk. Okay, so this is something which is could be tedious, but I hope you can get it done once, then you will know the whole principle behind soft update. So this is the trio. Let me actually put back these three things together. The first thing we learned on Tuesday is Snapshot. How do you actually just pick it up very quickly? And the second thing is what we call background FSCK. So background FSCK, remember I said, if I'm going to do a foreground FSCK, this means that we're going to wait for a long time. So the idea of background FSCK is essentially you take a snapshot while you're using the file system. I'm actually going to run the FSCK against the snapshot whenever CPU has any cycle for me to do that. That's the idea of a background FSCK. And the thing is that, well, then the remaining issue is that, well, how do I make sure that the file system is still safe to use while you're running the background FSCK? And the thing is that here's a property. Remember, we talked about in file system consistency check, if we can make sure that the block consistency, they don't have 1-1, and the file system and directory consistency, they don't have D greater than L. As long as I can prevent this two, that means my file system is actually safe to use. And I might have some disk block or file that's actually need to be garbage collected, but don't worry, the background FSCK is going to do garbage collection in that case, while soft update is preventing this two from happening, so allow the user to be able to directly use the file system immediately. Okay, this is the relationship between these three things, why they have to work together as a team to actually make sure we have a file system that's actually fast, that's actually can sustain against any kind of crashes, and it will eventually recover all the resources that's actually lost in this process. Okay, so that's the trio. So now we're going to focus on the first one, which is how do I actually do that? Soft update, how do I actually prevent 1-1 and D greater than L? Okay, so we know this problem, 1-1 and D greater than L. This is the things we need to worry about. So I'm actually going to actually talk about the first thing. Okay, so let's say I want to delete a file. Okay, assuming I want to delete a file, which means that I'm actually deleting a file in two different places. One, I'm deleting the file in the cache memory, in my file cache. And the second deletion is on the hard disk. So to complete the whole deletion that I have to delete eventually on the hard disk, then the file need to be, then the deletion operation is actually complete. Okay, that's what we are trying to do. So the first question I want to ask you, if I want to delete a file, what kind of what metadata I need to modify? Data or metadata I need to modify if I want to delete a file. Can someone help us to say, you know, what kind of metadata if you want to delete it, a file?
Probably direct and nlink.
Okay, so there is, when you delete a file, you have a direct, which is directory entry, need to remove that file. That's excellent. And you probably need to delete the inode. When I say delete the inode, it's really just make the inode become available again, right? And then to modify, erase all the information on the inode. That's great. There are two other data structures you need to remove. One is the free block bitmap, because once you delete the file, all the blocks from that file become available, right? So you need to modify the free block bitmap and such that you will make sure those blocks can be used for further use for file operation storage. And the fourth data structure you need to modify is actually free inode bitmap, because you remove a file means that now you have a one inode space that's actually available for you to use. So therefore you need to modify the fourth data structure, which is the free inode bitmap. So you have this four data structure: directory block contain the file, and inode block, the bitmap for the free data block, and also the bitmap for the free inode. Okay, you have four different data structure. Are we all agree on this? You have a four data structure, right? Okay, so when I say four data structure, means that let's assuming each of the data structure, just in case, they only actually involve one disk block. So you have a one disk block, which is directory disk block. You have a one disk block, which is inode block. You have a one disk block represent a particular location for the free block bitmap. And you have a one particular block for free inode bitmap. Okay, so you have a four disk block. This means that you have a four blocks of memory in the memory as well. So now remember, you have four blocks, that's we call a dirty block, in the memory, and we have a four blocks to be modified in the hard disk. And when I do deletion, what I mean is just moving these four blocks from the memory to the four blocks in the hard disk. Does that make sense? When I do a deletion, I'm just moving this four from memory to the hard disk, right? Everybody understand what I'm saying? Okay, good. Now my follow-up question, if I'm going to write four blocks from memory to the hard disk, my question for you is that which block should I write it first? Remember I said in self-update, the order is very important. So it means that between among these four different blocks in my memory, that I need to actually write back which one should go first. I mean, the reason I said which one should go first is because I could crash anytime. I could crash before I even start to write the first block, or I can crash in between first and second, or maybe even in the middle of the second block when I'm writing back to that. And then, or I can crash anytime when I'm writing the third block and the fourth block. And the thing is that what I want to make sure is that I actually want to write this back in an order to the hard disk, regardless when it crash. I will make sure I won't have D greater than L. I won't have 1, block inconsistency. So I want you to think about this. Okay, why don't we do this? I'm going to send you guys to the blackout, Let me see what I can do here. I want you to discuss about this a little bit among yourself. I'm going to send you to the breakout room. So you can actually chat a little bit, discuss among yourself about what you think should be the order of this four. So essentially is this four kind of data structure, that which one you need to actually be able to send it back first, okay? Let me see. Stop sharing. Blackout room. I'm going to assign you to, let me see. I have 48 students. I'm going to assign you to 10 different rooms. Okay, you have about 10 minutes to talk about this. Hey, Max, are you here?
Meeting is being recorded. Being recorded.
Okay, so I hope you have some good discussion in your breakout room. So let me ask you, among this 4 block, so this 4 block is directory block, inode block, and then free block bitmap, and also free inode bitmap. This 4 data structure, 4 block, I need to write back to my hard disk. This is actually trying to implement deleting a file. So in this case, which block should I write it back first?
Professor, we think it is the inode block that should be written first, followed by the inode bitmap.
Okay, between inode bitmap and the inode block, which one should I write first?
Inode block.
Okay.
Because if the system fails while writing the inode bitmap, then after writing the inode bitmap, then it might point towards a garbage inode block.
Okay. Okay, so let's actually just do a little bit of exercise between the inode bitmap and the inode block. So if I write back the inode block back to the original place, but I haven't updated the inode bitmap. So essentially what I have is that it could be possible that that inode is not free because bitmap is actually write down later than the inode block. So it's okay. It's just wasting some inode space, but I will never have the other way around, which is the inode hasn't been updated, but I actually already updated the inode block, inode bitmap, and then I messed up with the inode situation. Okay, that's good. So the order should looks like this, if you actually make sense. The order should be the first one you need to update is actually directory block. So after you're done with the directory block, then you actually do the inode block. And then you actually update. It doesn't matter between the free block bitmap and the free inode bitmap. It doesn't matter which one goes first because they are not depending on each other. Does this make sense to all of you? On deleting a file.
Oh, but that was the discussion not about creating the file?
No, the discussion about deleting a file.
Oh, okay.
Did I say deleting a file? Yeah, this is deleting a file. The discussion is when you delete, creating file is somewhat different. but deleting the file, I just want to make sure that all of you understand that this concept of the ordering about which block need to be write back to the hard disk, from memory to the hard disk in this particular order. In particular, just want to let you know that this too is important you have this order, like this way. Because if you didn't write the directory block before you write the inode block, it could be that you still have a file which in the directory entry, but the inode has been destroyed already. So which means that that entry is actually in the directory still there, and somebody actually click it, try to open that file as executable or something else, and there is a totally unpredictable outcome that might happen because you actually trick people to click on a file or open a file that's actually not supposed to be there. Any question? Okay, so I'm going to move to the next picture. So this is about deleting a file. Now I'm going to do a creation of a file. I'm going to create a file. And now I'm actually going to ask you the same thing. What are the order about the file, the block you need to actually write it back to the hard disk? It's always the same situation. We're going to worry about that. And the thing is, because it's so similar, but it's exactly opposite, I'm just directly show you the answer. The answer is actually like this way. On creating a new file that you're going to, by the way, when you create a new file, I haven't included the this block because this block is after you create, you're going to write to the block. So we're not worry about that right now. So we just worry about the three data structure, inode bitmap, and the inode block, and the directory block. And the order is going to be exactly opposite. You're going to write the inode bitmap first, and then you write the inode block, and finally you write the directory block. I'm not going to tell you the detail because the logic is exactly the same, and the logic is exactly try to prevent D greater than L and 1-1 situation. Okay, so just if you understand the deletion, then the creation is just flip your mind and you can deal with that. It's still from memory to the hard disk. Okay, so I'm going to talk about the next subject. So now you understand deletion and creation. There's a few rules about if you read the original paper or read, I mean, the paper we actually assigned to you, it basically say you should never point to a structure before it has been initialized. That's for creation. And you should never reuse the resources before nullifying all previous pointer to that. That's actually for deletion. And then there's a third rule that's actually handled more or less like a move or rename option. It's the combination of a deletion and a creation. And I just want to use one example to tell you about this. So for example, I'm actually trying to rename from the old name to the new name. This actually means that I'm actually going to move from this Duran to the other Duran. Okay, I'm going to move. So this means that I'm actually going to remove this one and I'm going to create this one. So in some sense, that's how we implement. And the thing is, how do I actually rename a file? And in this case, I don't even need to worry about the free block bitmap or free inode. I'm just going to looking at the directory block and inode block. Because right now I have two blocks. They both involve adding and removing. And the order looks like this. Does that look okay to you? Add the new name to the directory and then write the inode link count to the inode block, and then remove this from the directory block. So you're going to write the same directory block twice, and then you actually do the end link count -1. Does that look okay to you? So this 4.
Professor, why not just replace the name? Why should we manipulate the link count?
It depending on how you implement the situation. It's sometimes if the two name is not in the same directory. If it's a move, if it's the same directory, yes, you can do that. But usually when people do rename, they also think about, oh, I can actually rename in a different directory. I'm renaming not just the file, but rename the whole file path name. Then that's why you might have a situation looks like this. But in any case, this is actually wrong. This order is wrong. The correct order should be like this. The correct order should be like this, because remember, one is essentially is deletion. One is creation, one is deletion. In the creation, we actually update inode first, and then you update the directory entry. And deletion, you actually update remove the directory entry first, and then you remove the link. If you remember the previous, they're exactly opposite. So the correct order is modify the inode, add a new name, remove the old name, and then you remove the link count. And if you look at this case, you understand, you try to do crash in each of the case, you realize your file system is still consistent. That's the 3 rule of the soft update, okay? Any question? Okay, so now I think we're moving pretty fast. Before the end of the day, I'm going to tell you the last case, which is a fairly interesting case. Wait a minute, I'm already over time, is that right? Oh, wow. Wow, I thought I have until 3:20. I'm sorry, I'm already over time. What I want to do is that, no, I'm going to end it here. Yeah, sorry about that, just a moment. Okay, so any question before I finish today's lecture? Any question?
So I have a question.
Sure.
When we create a file, does that also include the data to be returned to the file, or just?
Yes, that's data block. So essentially, when you create, I mean, just example, when you for file deletion, for file creation, when you have a data block, right? So you need to actually write down those data block to the hard disk before you write the pointer, which is the inode. So inode is a pointer between inode and data block. For creation, data block first, and then inode. That's the principle about this 3 rule, saying that you need to never point to a structure before it has initialized. So that's applied to data block as well. And in the removing is opposite direction. Okay.
Professor, do we have a discussion class tomorrow?
Yes, we will have a discussion class tomorrow. We have a discussion tomorrow, but today I just want to let you know that let me turn off the recording first. Hold on 1 second.